So I'm not actually sure where everyone is on the math behind this, so I'm going to start with just some essentially an introduction to kind of probabilities and statistics, or a review if this is all familiar. Basically, all of the kinds of objects that machine learning manipulates are statistical objects. So having some basic terminology is important. So usually what you're doing is you have some data, and that data has some randomness behind it. So you don't have a guarantee, like there is some rule that if you learned it, you would get 100% ability to predict. Also, even with that, the data associated with different things you're trying to predict is going to be distributed in different ways. So at the end, the machine learning algorithm often is going to output probability distributions of the different possibilities associated with your data rather than a distinct, red, blue, cat, dog kind of classification. And a lot of the things that the machine learning algorithms are doing, you can actually frame it as trying to optimize one probability distribution against another. So you have some target distribution and you're trying to match that distribution rather than you have some target label and you're trying to match that label. So basically, there are different kinds of objects in terms of probability distributions. The most general thing is a joint distribution. So if I just have a bunch of variables, it's just for every pattern of occurrence of those variables, it's what is the probability of that particular pattern of occurrence happening, or what is the probability density as another object, which is to say, in a certain window or a certain size, if I integrated the probability density over that window, that would give me the probability that the observation is going to be in that window. Then what I can do if I have a joint distribution is I can project it down onto one variable or another. And that's basically saying, I'm going to assume all of the other variables take values according to that distribution, and then I'm just going to sum over them, and I get a probability distribution with respect to only one variable or a subset of the variables, and that's called a marginal distribution. So here you have the joint distribution, and up here I basically summed out all of the y, and here I summed out all of the x, and these are the distributions projected onto those axes. So these things can be interpreted in various different ways. If I have some kind of underlying process, like something that repeats and it's always the same, so I'm flipping a coin and I keep flipping that coin, I can talk about the probability that that process is going to give one output or another. So you could think of like a process is I have all the cats in the world and I randomly pick a cat and I get a cat image. So I've got a probability distribution over cat images, given that I'm performing this process of randomly picking a cat, taking a photograph from a random angle, etc. But I can also say, we're using the same language, that a probability represents my best belief about the world, but it's about some actual concrete thing which has a true answer, or which might have a true answer. So like, if I have a photo and I'm not entirely sure what it's of, I might believe that it's a cat or believe that it's a dog, and I might have some kind of willingness to bet. How much would I bet that this is a cat? How much would I bet that this is a dog? And as I get more evidence, even though that is actually a photo of a cat or a dog, my beliefs could change. So in those two particular views, there are differences, but they're also a little bit interchangeable. And a lot of the time, it's not entirely clear what a given probability means, but you can kind of use a probability to refer to one or the other. So for example, if we're talking about the coin flip, since I have a process, so I have an underlying probability that I get heads or tails, that would lead to me having sort of prior belief. If I knew that this coin was biased, then maybe I would expect that 80% of the time the coin is going to be heads and 20% of the time it's tails. If I do the process, I can measure that 80-20 split just by repeating the coin flip. But also when I'm inferring, like if someone flips the coin and hides it, and I'm inferring about the state, that's also the same belief that I should start with about what it is. So that's the kind of connection between these two ideas. All right, so one of the objects that is used quite a lot is a conditional probability. And this is basically saying, all right, there is some underlying probability of this generating process, or of the outcomes of this generating process, but now I have some evidence. So it's not just that I have a coin flip and I don't get to see anything, but I have a coin flip, the guy looks at it and he says, okay, you want to bet, and then he makes a bet or something like that. And then I can say, all right, I might believe 80-20 based on just what I know about the coin, but when they say, you know, I'd like to bet heads after they looked at it, I can probably say it's heads, right? So I have this, the evidence modifies my belief or my expectation. And so when I calculate sort of what is the probability given that evidence, then I'm conditioning on a specific value of that evidence variable. So if I started with the joint distribution, right, this is P of X and Y. And if I knew that X was a certain column in here, I could say, what is P of Y associated with that column? So the marginal distribution is the sum over all Y, over all the values that I'm projecting out. But the conditional distribution basically take a slice and then normalize it back so that the probability is sum to 1, right? So if I said, oh, well, this is the joint distribution, but my X is out here somewhere, right? It looks like the probability is basically 0 there, but if it's just some small value, it probably looks like a Gaussian around minus 0.28 or something. Then if I did the conditional distribution, that would actually just be a probability distribution, but only associated with the values in that column. And what that ends up looking like is something like this. Right, so here I've done the probability of Y, that is the vertical value, given X. So even though the joint distribution is almost 0 out here, the conditional distribution still integrates to 1. And here, P of X given Y. So it's important to note that when you have a machine learning algorithm or something do an inference like this, it's not actually telling you the first kind of probability, which is the actual true probability associated with the generating process. It's telling you an inference. So it's a best belief given the evidence that it has, and that evidence includes the training set and the methodology and selection of the algorithm and all of that. So when you interpret this in a scientific context, it might be tempting to say, we're training a machine learning algorithm to classify life versus non-life on exoplanets or something. We see the spectrum, and the probability that there's life there is 70%. And you shouldn't say that, right? It's that given the evidence and what we trained on and the context of how we actually came up with this, we believe, to the best of our knowledge, if this were drawn from a similar kind of distribution, it would have a 70% chance of being among the samples that we use that have life in it. But that's not a true, it's not a physical property of the universe that there's a 70% chance that there's life on that exoplanet. Okay, so what we want is usually these conditional probabilities. How do we get them? So if I had a parameterized physical model, that is, if I had something like an n-body simulation, or I had some kind of biological simulation with biological networks or something like that, I could say, here are all of the different things that could vary about reality. And for each value of those things, I have a certain distribution of outcomes that they produce, right? If I put the planets in this position, I get these orbits, or if I have the biochemical network with these input fluxes and output fluxes, I get this kind of distribution of reaction rates or of metabolic products or something. And so if I get that distribution of the outcomes given the parameters, what I can do is I can kind of invert that. And I can say, all right, take every possible value of the parameters, and I have some prior belief over those parameters, which I need in order to use this technique. And then I can say, okay, since I know the probability of the evidence given the parameters, I can figure out the probability of the parameters given the evidence. So that's essentially given by this. And this is just a change of basis, right? So when I multiply P of X given Y by P of Y, I get the joint distribution. Right? This is P of X comma Y again. And then if I have P of Y given X times P of X, I get the joint distribution. So this just says the joint distribution is equal to itself. But the convenient thing here is that I can actually flip back and forth between a view that is centered around, what is the evidence I see as the given, or what are the parameters I have as a given. And I can go back and forth between them and use that to figure out the conditional probability that I want. The problem with this is you need a physical model. And a lot of the time, the world is so complicated that if you were to write down a physical model, it's incomplete or it has errors. And those errors are not accounted for by this kind of formalism. So if the parameters include the true physical model, that is the laws of physics or the actual laws of the system that you're studying, this would be fine. But if your parameter space actually doesn't include a point that corresponds to the real world, then the behavior of this is it becomes a bit ill-defined. If your thing is, roughly sort of, if everything is kind of smoothly dependent on everything, maybe it's okay. But if you had something like chaos, then you could be arbitrarily far off and still believe with very high confidence that, in fact, you knew what the world was. So what can we do instead? We can take a kind of empirical approach. And this is what most of the modern machine learning techniques are centered around, although there are a lot of ways to come back to this kind of thing later on. People now are developing sort of Bayesian versions of a lot of the more just directly empirically driven ML. So what we want to do is say, okay, we want to match this conditional probability distribution, and we've got a lot of examples from the world of both the evidence and the target. So we're just going to try to make the one distribution be the same as the other distribution. And all we need to do is find a difference between those distributions and minimize it. In order to do that, I want something really, really general to model that queue of target given evidence, that sort of distribution that I'm creating with the machine learning algorithm. So I want it to be able to represent any possible function. And then all I have to do is do some kind of gradient descent or optimization process until the two distributions agree. Well, not all I have to do, but at least that's the idea. So one way we can do this, there's an object called the KL divergence, and this measures the difference between two probability distributions. And just to give you kind of an idea, with this kind of thing, if P is Q, right, then this log is log of 1, which is 0. So the KL divergence is 0 when the distributions are the same. And if the distributions are different, then this thing is always going to be positive, which might take a little bit of fiddling to see. But basically, it's if we got that to be 0, we would know that we match the distributions. And we're not going to actually ever really get it to be 0, but we can get it small. Now I just need something to match to. So I have data. I don't have some nice, analytic function. So what I can do is I can construct something called the empirical distribution. And this is just a delta function where every data point is. And so wherever I have a data point, I've got a little spike. And if I integrate a spike, I get 1 over n, where n is the number of data points. And this is literally what I know when I have a data set. I could interpret this that it should be smooth, it should be something else, it should look like I've kind of averaged it, but that's all me imposing some kind of prior on it. This is just the raw data interpreted as a probability distribution. So conveniently, it's annoying to take the like if I had data and not analytic functions, it's annoying to do this when I have stuff inside the log. But conveniently, Q is only showing up in the log and it doesn't show up outside. So what I can do is I can just say, oh, the sum over P of X log of blah, blah, blah. The sum over P of X is just the sum over all the data points, 1 over n times the sum of all the data points. So that kind of pops away. And then I'm left with the sum over the data points of log of Q. So this thing here is going to be the object that for most of the time in machine learning, when you want to do a classifier and assign a probability to every possible class or something like that, you're just going to be optimizing this object. So it's called the cross entropy of log loss. Log loss is usually if it's binary, if there's only 2 classes, and cross entropy if it's general. So this is kind of an example of what this function looks like. Here I have some coin flips, and then let's say in this case there's not much to model because I don't have 2 variables, so I just have a probability of heads as the only thing I'm trying to fit, which is convenient for plotting it. So this log loss ends up being this thing, and that's this function here. You can see it goes to infinity. Well, maybe you can't see it, but it does go to infinity at 0 and 1. And then it has a minimum, and that minimum happens to be at exactly the empirical ratio of heads to the total number of flips. So this kind of shape, this kind of optimization is going to be really, really common. There are going to be some numbers if you do a lot of machine learning that you just get stuck in your head. Log 2, which is about 0.693, is going to just be hammered over and over. Because if you had something where you had a conditional probability, but it turned out the thing you were conditioning on didn't matter, and you had balanced data, your classifier will say, oh, 0.693, and that means that it failed. So it's like powers of 2 if you're a programmer. Okay, so what does this let us do? Why should we care about this log loss, or do we just hide it inside the machine learning algorithm and move on? Well, it's not 0 at the optimal value, right? In the coin flip thing here, it actually got down to 0.75. And that residual is meaningful. Right, so maybe it's not clear where that residual came from, because here I said, oh, if the KL divergence is 0, I match the distributions. But you notice how there's this constant term that pops out, and that constant term ends up being the entropy of P, I think. So we basically don't directly work with that or resolve that constant, but if I actually optimize it and see what the residual is, I can actually conclude, oh, well, this residual is the entropy, the residual entropy of my probability distribution. So what does that mean? If I had coin flips and it was a 50-50 chance, then my entropy would basically be 1 bit, because it could be 0 or it could be 1 with the even chance. Or in order to tell you what happened from a series of coin flips, every coin flip I need to send you 1 bit of information basically to describe. But let's say the coin was 99% of the time heads and 1% of the time tails. I could come up with a way that would actually tell you the sequence of heads and tails much more efficiently than telling you each one with 1 bit. Because you basically get to know that, oh, this coin is 99% of the time heads. So I only maybe need to tell you the coordinates of where the tails flips are, and then just assume the rest are heads or something like that. And the amount that I need to tell you is that entropy. So the entropy is kind of measuring the number of effective equal possibilities that could still occur. If I have the entropy of the distribution, it's sort of how many things happen in that distribution. If I have the entropy in a conditional distribution coming out of the machine learning algorithm, it's telling me that even with all the evidence I have, how much do I still not know? So if I say, well, conditioned on all of this evidence, I've got a log loss of 0.1 on predicting whether or not this disease will occur or something like that. That's sort of telling me what are the different possibilities, or it's counting the number of possibilities left, even after everything I know that I just can't decide yet. I have to actually look at the world and see what happened up to that level. That residual entropy could be far, far less than if I didn't have that evidence. So what we can do with that is that we can say, okay, let's say I've got one model that predicts the occurrence of cancer just from the population statistics and not looking at any demographic information. I've got another model that predicts the occurrence of cancer given demographic information, another model that predicts the occurrence of cancer given, say, demographic information and a detailed health checkup or something like that. I can look at those residual losses, those residual errors, and compare them. And the difference is how much extra information I've gained by adding that new piece of evidence. So this starts to actually become a really useful thing for scientific inquiry, because now I can say, looking at this geological phenomenon, I could try to predict it and then predict it given some other thing that I think is somehow related to it. And that difference is telling me how much information I got about the phenomenon by looking at that piece of evidence that I want to evaluate. So this starts to become a way of actually seeing, it's still only telling you about correlations, right? So this is not a causal story yet. And in fact, at the level of the stuff we're going to get to today, I'm only going to kind of suggest that there are ways of making it causal, but generally speaking, you're working in correlations. But it's still kind of telling you how the information in the system is connected to each other. And in practice, of course, the machine learning algorithms aren't perfect. So the thing you measure isn't actually the information. But the nice thing about it is there's at least as much information as you measure. So it's a lower bound, and you can be sure about that lower bound aspect of it. It's just, there could be more that you missed. But at the very least, if you can predict this from that, you know that there was something there. Okay. Beyond the kind of log loss point of view, there are kind of practical ways that people measure accuracy. And now this is moving more to like, if I've trained one of these models and I want to deploy it in the world, what are the ways that I evaluate, should I deploy this model or that model? It's not always the best to say, oh, pick the model with the smallest log loss, because different kinds of errors might matter differently depending on the thing. So the basic split down for a binary classifier is you might have some label, and when the label is 1, you could predict 1, and that's a true positive. You could predict 1 when the label is actually 0, which is a false positive. You could miss a label that's 1 and say that it's 0 when it should be 1, that's a false negative. And a true negative is when it should be 0, you predict 0. And the accuracy is basically just what fraction of the time you're right about whatever you say. This is a pretty common thing. It's a reasonable metric when the classes are balanced. So if you've got 50% of class 0 and 50% of class 1, this is reasonably informative. And the other nice thing is if I had 1 million classes, I could still measure this number and I don't have to do anything too fancy about it. But it can go wrong in a couple of ways. So let's say this is cancer screening again. I don't know, I'm speaking on cancer as the example. And if I have cancer and I go in for a screening and they say you don't have cancer, that's really bad, I'll probably die. But if they give me a false positive, then I might be put out of it. But after a few weeks, I'll get over it. So I definitely don't want to treat my false positives and false negatives equally in that case. And there's a way that people dealt with it. This comes way back from, I think, World War II, like sending coded messages to each other or radio communications. So it has a very bizarre name, and it just stuck around forever. It's the receiver operating characteristic curve, or the Roc Curve, and I'm just going to call it the Roc Curve from now on because I don't think the words are going to be very meaningful for any machine learning application, but that's unfortunately what people call it. And this is basically just saying, okay, I want to use an algorithm that has some kind of threshold, ability to apply a threshold put into it. So maybe it's an algorithm that's giving me a probability associated with each class or score, but somehow I can rank my predictions from low confidence to high confidence on either the 0 or the 1 side. And then I can say everything above this threshold I'm going to call a 1, and everything below I'm going to call a 0. And as I move that threshold, I'm going to generate a curve. And that curve is going to have on one axis the false positive rate. As I make the threshold higher and higher and higher, I'm including more false examples as true. And then on the other axis is the true positive rate. And I also know that if I have the threshold at 0, I basically say everything is 0 and I don't care. So I'm going to have a 0 true positive rate and 0 false positive rate. And if I have the threshold at 1, everything is 1 and I don't care. So I'm going to have a 1 on both. So it fits within this 0 to 1, 0 to 1 range. And it's a monotonic curve. And what I can do is I can say, okay, depending on what I want, if I really, really want to avoid having false negatives, I want to maximize the number of true positives, and I'm willing to pay some amount of false positives to get it. So I can put myself at a point that's at a high false positive rate to get a high true positive rate. Or I can equally well say, this is like detecting a criminal or something from a database of people who are on wanted posters. And I really don't want to say, oh, you're this person who we're looking for, and they're not. But if someone gets lost, maybe it's okay. And then I would really want to minimize the false positive rate because it costs me a lot more to accuse someone or to pull someone aside and then have them sue me than to just let them be out for another day. So depending on where you put the threshold, you get different points. You pick one that suits your optimization, or it suits essentially the way that you're valuing your different kinds of errors. Okay. Sorry, that went probably quite fast, but this is a good point to stop for questions on the first section. Okay, should I just go on? All right. So that's the intro to sort of some terminology I'm going to use, but now we're going to get into something that's more like what is the actual workflow of working with supervised learning in particular. And this isn't going to focus on explaining how any supervised learning algorithms work, but I'm going to try to present this in a way that lets you treat these things as black boxes. And if you want to know more and get into it, you can. But I think it's important to kind of get that there's a separation between these things have been wrapped and standardized in code to such a degree that you literally can just use a new name of a function, see how it is, validate it, see that it works in your problem. And if you think about your problem in terms of, if you design a problem in such a way that you don't need to know what's going on inside the algorithm, you're more likely to have problems that machine learning is actually appropriate for. Whereas if it's really, really important, whether it's a random forest or an SVM at some level, then maybe actually that's not the best problem for this kind of technique. So there's a couple different categories that people place for machine learning, and it's basically driven by what you have and what you want. The easiest thing is supervised learning, and that's what I'm going to mostly talk about today. And with supervised learning, you have a problem where you have examples that you are happy with. So you've got inputs and you have outputs, and you as the person deciding to do this problem declare what that relationship should be by giving a lot of example data. It's not as useful for exploratory stuff where you have some inputs and you don't know what the output should be, but you want to get a good idea from the network or from the algorithm, although that kind of work can be done as well. And that moves from supervised learning to what are called semi-supervised or unsupervised learning. The difference between those in semi-supervised learning, you have something. It's just not exactly the thing you want, and you're trying to indirectly kind of get at a thing that you actually want by sort of implication. So, for example, people do things called embeddings, and with embeddings, you might say, I want to understand the structure of the English language, but I don't have an output that says, label, this is the structure of the English language. What I might have is I might have the occurrence of words together. I might say, I want to have some representation of a word that predicts what words are going to follow it and what words come before it. So it's a thing I can predict it, but it's not directly the thing I'm trying to get. And I hope that by doing this, the structure that I learn will actually be useful at getting at the thing that I want due to that indirect relationship. And fully unsupervised learning is basically, you don't even necessarily have that. You just have data and you want to find the inherent structure of the data, and there's not this kind of hope that you can apply a learning thing that would be useful for your task. And these are basically in order of difficulty. So supervised learning is very easy. Unsupervised learning, there are techniques for, but the further down you go, the harder it is to interpret, the harder it is to actually get a really concrete result out. But all of these things are actually really useful and powerful too. Just for sake of stuff we can fit into 2 days, we're mostly going to focus on supervised learning, and maybe at the end tomorrow we'll do a little bit about embeddings. Okay, so one of the things is I think probably the most important thing is to get an idea when to use these techniques rather than how to do it. Because the kind of workflow for machine learning is very different than usual scientific inquiry. Basically, you need to be able to find a correct answer, right? It's not like I'm going to test a hypothesis with this kind of stuff. That's if you go there, or I'm going to discover something about the real world, right? This is not a vehicle for getting truth. This is a vehicle for implementing some process that you can define, such that instead of having a student do it, by hand for the next 10 years, and then the entire system relies on this one student who's mastered being able to pick out craters. You just have a box of code that you send anyone who wants to detect craters, and it becomes standardized. So, yeah, you have to know what you want already, and you can't have that be too uncertain. The other thing is that these things will they basically work when what you're using it for is the same as what you train it on. So if you say, okay, well, I'm going to make some craters in a 3D rendering program and then use it on the moon, I'd say, okay, you can do that, but all of your guarantees are gone. Right? You're now training on a different distribution than you're actually applying it. So any number that you get out to validate your method, it's uncalibrated to reality. So it's really important to try as much as possible to be using the actual kind of application that you intend to deploy it on as the source of training data. It's not insurmountable if you can't do that, but everything gets a lot more complicated, a lot more woolly, and you can no longer have that kind of degree of confidence that you've actually validated the thing. The other thing is that all of this stuff that I'm telling you about is measuring correlation. And you can ask causal questions, but you need to use the same kind of techniques you use in designing experiments to get at causality if you want to get at them with machine learning. If I look at some big data set of the stock market or something, and I see that there are these, fluctuations that are very, very predictable 99% of the time, it doesn't mean I can cause them. It doesn't mean that if I do interventions in an investment strategy based on that I'm actually going to get that I can drive the stock market where I want or something like that, right? I could do those interventions and suddenly I'm now drawing from a distribution that my training set because I wasn't training on the intervention distribution. So if you want to get a causation or process, you have to be a lot more careful and do something a lot more sophisticated than just throwing a machine learning classifier at it. But there are ways that kind of research can be done. It just it's not as black box. It's not just throw everything at it. So there's an example that we did, I guess, a ways back now. There's a lot of earthquake recordings or seismic station recordings, and it's important to get the time of arrival of earthquake events from many different stations to do tomography. So you can go and you can look and see where is the spike in the time series, and a student can do that. And if the event is really clean, it's really easy. And if the event is dirty, a human can still do it, or at least people have some sense of like being able to say, oh, I can't do it here, so throw this data out, or yes, I can do it here, I'm confident even if it's noisy. So there is a data set of hand-labeled data that people have confidence in. And the use case and training case are basically the same because you've got the seismic stations that you're looking at, and you're going to be looking at those seismic stations in the future using the same algorithm. So it's basically drawn from the same distribution. You also don't really care how you identify where is the spike in the seismic map, right? What you want is timings that are good, and you want to quantify the error in however you get those timings and things like that. But if you get there with a student, or if you get there with a random forest, or if you get there with a neural network, it kind of doesn't matter in the end. I mean, it's nice to know for the machine learning side, but the science won't change. So that's kind of a solid example. On the other hand, let's say I was doing something in medicine, and I really want to figure out how I should treat someone using machine. I want to use machine learning to figure out, oh, here are all of the factors that contribute to the state of disease, and I want to tell someone, how do I change your lifestyle so that you don't get cancer? How do I change your lifestyle so that you don't have heart disease, things like that? Well, as I said before, the problem is that the training data comes from the no intervention case. So I'm just taking people from the population, and then I'm trying to use this to figure out what's happening in the intervention case. But this model would say, if I want to stop someone from smoking, I should cure their cancer. They're exactly the same statement from the point of view of the model. So I'll get garbage out if I just apply that naively. I would have to do something like random trials. I would have to do interventions and train it on the intervention data, and then I could basically compare different intervention policies using the algorithm or something like that. But if I just take it on the population as a whole, I will get nothing. Okay. So this is kind of what the outputs of these things look like. If I have classification, I might have data with different labels. And then it's going to give me a decision boundary. If I have some kind of continuous values that I want to predict, like the price of an apartment in London or something based on the neighborhood it's in or things like that, I'll get a curve fit. So this is a regression. And then a very general thing that I can do, as I suggested with the whole thing about the log loss, is I can just ask for probabilities. So here it's a bit harder to visualize. I have the same data here as here, but now at this point, the network will output, say, probability of red, green, and yellow, probability of red, green, and yellow, or red, blue, and yellow, probability of red, blue, and yellow, probability of red, blue, and yellow. So every point in the space now maps to a distribution of the possibilities. And you can actually use this kind of probabilistic thing both for categorical labels, if I have like a discrete distribution ABC, or I could even use it for regression, where this distribution might be some mixture of Gaussians, or it might just be a continuous function or something, some arbitrary continuous function or something like that. That would tell me the probability of each value that the regression could return at that point in space. So like in the regression example over here, it's just fitting this kind of sine-like thing. But the probabilistic version of this would fit essentially a Gaussian around every x value, showing me both the mean and the standard deviation and even the higher moments if I use an algorithm that could actually model that kind of thing. So I have a particular soft spot for just doing everything with probabilities rather than these kind of more reduced things, but these are also useful in a lot of cases as well. The probability is sort of the Swiss Army knife of this set. All right, so one of the concepts that comes up quickly, it's not just enough to match these distributions or to match the training data, because what you'll find is that, well, of course, I have an infinite number of parameters in most of these machine learning models, or I have the possibility of having an infinite number of parameters. So I can just put a line through every point. Okay, I'm done. And if I do that, I see something like this thing on the left, where, okay, yeah, I've got a sine wave here, but the regression has, very, very accurately passed through every one of the training data points, which are the large blue dots. And I find if I ask of anything other than exactly the value of the function at one of the training data points, I get no real predictive power at all. So the way people refer to this is whether or not the algorithm generalizes, or what are the generalization bounds of the algorithm. And there are ways for certain kinds of algorithms that you can actually even write down like hard rules of how much you would be able to prove that this could generalize. Those in sort of modern machine learning techniques have become very weak bounds because they rely on you having fewer parameters than data. And the shift towards neural networks means you have generally many more parameters than you have data. But it does exist. There is some theory behind that. However, in practice, what you can do is you can actually use validation and figure out exactly how you have to tune the number of parameters you have, or different ways to kind of push the model not to just fit every point, but to try to make smooth curves or things like that. And you can use that to essentially find an optimal middle ground between this kind of overfitting where I pass through every data point and this underfitting where I just give the average of the data set or something like that, and I start ignoring inputs that could have been informative. So what this is going to lead to is that it's not just enough to take training data and show a good score on the training data. I want to actually take my data and split it. Training data, then I'm going to have something that I'm going to use to actually find that middle ground. Then finally, I'm going to have something to use to make sure that even after I've found that middle ground according to my data, I have some way of evaluating how well this algorithm will work when applied to new data from the world. So that leads to this kind of training, validation, and test set split. And generally speaking, there's a lot of factors behind choosing the size of these different categories. If you have a limited amount of data, you have to work with what you have, of course, but the bigger you make the validation set of the test set, it's like any sampling process. Your error in estimating the accuracy of your model would go down. So there's an error bar, and you shrink the error bar by making those things big. But the other consideration is that usually, if I think about the validation set, it's like fitting a metal model, right? I have my model and it has some parameters. When I train the model with one value of the parameters, another value of the parameters, another value of the parameters, I end up at different points in this space. But there are far fewer of those hyperparameters than there are internal degrees of freedom of the model. So I don't need a validation set that's anywhere near as big as my training set usually. Usually I want to get as much into the training set as I can afford while still getting statistically reliable reads of relative performance of different parameter choices with validation and test. Of course, this is very nice. If I have infinite data, I can do whatever I want here. But for a lot of problems, we have almost no data compared to what these things would need. So, I could say, okay, a good data set size, I'm really happy if someone gives me 1 million data points. Can you go and measure 1 million organisms' genomes, or 1 million mass spec, or find me 1 million planets? I want to know about the general properties of planets. I need 1 million planets. And I might be able to get 4,000, but actually in practice, if I want them to be complete entries, I'll have like 600 or 700 planets. At 700 planets, I don't really have that much freedom to just throw away 25% or 30% of my data set for training. I really need everything I can get. So when I'm in that world, I have to use something called cross-validation. And the idea here is that you just take different permutations of the data set and train the algorithm multiple times on different permutations, and then look at the statistics over those multiple cuts to try to get the validation set so that you don't actually need to throw away that You still really should have a separate test set after all of this. But even in some cases, you can't even do that. And you can use the same kind of cross-validation strategy in that case to get at least some idea. So you don't have to give up if you have 70 data points. So one of the caveats of this is, as you change the number of cross-validation cuts, you might think, okay, more cuts, I get better statistics. But when the number of cuts is very large, each of those validation sets has very few points. And you can easily get into a situation where the number of points in a validation set is comparable to the number of labels. Let's say that exists, the number of types of labels. So let's say I've got 4 kinds of labels and I've got 10 points. I might have one of these batches, label 0 appears 30% of the time, and another batch it appears 50% of the time. And the actual probability in the underlying data is maybe 40%. When that starts to happen, even if I get more and more and more of these batches, so that I get better averaging and I get kind of better statistics, at the same time, each batch becomes lower quality. So I have a diminishing returns where just doing that will not get me everywhere. I can't just take an infinite number of cuts until I have a nice smooth statistics no matter what. There's just so much information in the data set that can be squeezed out with this, and you can push it, but you can't push it forever. Okay, so one of the nice things about framing it in this way is I haven't said anything at all about specific algorithms yet. All of this is really general pipeline workflow kind of stuff. So you can actually set up an entire workflow for this that doesn't care what algorithm you're using. And then it's literally just switching a line of code, changing the name of the function to do everything again. As long as it has a kind of standardized problem setup. And there are a couple of different kinds of standard problems that people do, but a really common one is tabular data. And here you just have a bunch of features. And for each data point, so obviously the data should actually be on the one off, so each data point should have feature 1, feature 2, etc. But you just have a matrix, a data matrix. And then you have target values y. So you split these into training, test, validation, and test sets. And here's some sample code to just show you can do this kind of, with pandas to load in a CSV file, and then just use some pre-baked test set splitters from scikit-learn to split this in various ways. There are ways that you kind of try to normalize the statistics of every batch. That's what the stratified shuffle split does. So that tries to make it so you have the same number of each kind of label in each of your cross-validation batches. But it's just, grab code, throw it at the data, and you get different cuts. And then if you want to just train every model in scikit-learn against it, you can do that. You make a list of models. For each model, you instantiate a classifier, you fit it, you predict, you score it, you print the result. And now suddenly you don't really have to care if this is elastic net or random forest or support vector machine or I don't know what else I have in here. I have too much stuff in here. Some of these are redundant with each other, but it doesn't really matter to the code. And since you're using a validation process, you don't actually have to think like, would I expect this kind of model to be better on this data, right? You let the data tell you. And as long as you trust the validation process and you validate in a way that's consistent with how you're going to apply it, then that should be fine. So I mentioned hyperparameters a couple of times, and here's an example. This is from a support vector machine, which is one of the kinds of things that you can fit. And it has 2 important hyperparameters, which means that there's some extra constants associated with how the model is being told to work. In this case, what they happen to mean, this C value is essentially saying how much should it try to make so this thing is essentially fitting like some kind of sum of functions, right? As some alpha I times a function to make this decision surface. And if C is very, very small, it wants to make the values of those alphas very, very small. Or basically to make as much as possible to have the alphas be 0. If C is very, very large, it can do whatever it wants. And then this gamma is essentially saying how many of these functions there are, what is the sort of spatial resolution of this function. So if gamma is very, very large, then the functions are little tiny regions, and if gamma is very, very small, they're big blobs, right? Two numbers, I can interpret them, I can plot how things vary. And this is just giving me visually the same kind of thing as when I showed the overfitting of the sign data. But like, I can also kind of summarize this and say, really what I care about is, am I overfitting or underfitting? And all of these parameters are just kind of moving me around in the space. Here I have 2. I might have something where I have 50 parameters or 100 parameters, and I'm not necessarily going to be able to look at it and pick the right ones by hand. Right? If I'm designing a neural network with 20 layers, and each layer has a width, and I also have regularization constants for each layer and learning rates for each layer, and I've got some other activation function which has extra constants in it, suddenly this becomes something where, yeah, maybe I have some good instinct for default values, but if I really want to optimize it, I need to optimize it somehow. So for this, we can come back to cross-validation again. And if I just try different hyperparameters, cross-validate against the validation set, I get a bunch of scores, and I can just pick the best one. So if I only have a few hyperparameters in grid search, which is just trying every C value, every gamma value, etc. So C equals C equals gamma. That's fine. As long as I'm in 1 or 2 dimensions, this is pretty efficient. If I have higher dimensional space to explore, so I have 4 hyperparameters or 20 hyperparameters, this is exponentially expensive. Right? If I had to add a 3rd axis, it would be terrible. If I had to add 8 axes, then just go home. But it turns out that I think I go 3 or 4 dimensions and higher, random search is actually much more efficient than grid search. So you basically just pick random points in the space, and that's a reasonable way to find these things. You can get fancier than that. There are ways that actually will do gradient descent or will do inference over the space of hyperparameters. And for some applications, you might need to go that far. But for the most part, that's kind of like, you start to get diminishing returns for that kind of thing really quickly. So that's more of a research program in itself to discover an efficient way of finding hyperparameters rather than something you would do for a problem that you're actually solving. And so, here's some examples. There's, again, in scikit-learn, pre-baked code that will do the search for you. So you just pull up grid search CV, and it will do the cross-validation, splits internally, and everything for you, and it will just spit out optimal values or the top 5 options or something like that. Okay, that's tabular data, or well, that was tabular data. Now we're going to get to something that's not quite so easy.
When you do the grid search,
yeah,
it's actually running the network you've done to do that. I can't see it in code.
Yeah, so in this random forest classifier or SVC is the model, and then you pass the model into this, and it's going to initialize the model with parameters randomly sampled from the table.
So you're telling it that your parameters are max features and samples max depth.
Yeah, and you're telling it the values that you are willing to search over.
Okay, and it will just pick through those.
Well, and it'll click through all of them. Grid search here, it'll pick 20 random combinations and tabulate them and tell you the best parameters and the score their other hidden fields. Yeah, and there's also in the at the GitHub there's example code implementing this before, which we'll get to this afternoon. Okay, so we're done, I guess done with tabular data for now. Tabular data is not everything, right? Sometimes, or most of the time, if I'm doing something interesting, I'm going to have data which is somehow idiosyncratic to the problem I'm trying to solve. It doesn't necessarily, get collapsed into a table. There is some kind of relationship between data elements that I really want to take advantage of because I know that this isn't just a table; it's an image, let's say. And I can get I could, of course, just collapse the image into a table, right? I could say pixel in the upper left corner, red color, pixel in the upper left corner, green color, et cetera, et cetera. And what I find is if the image is very small, I can do that. Maybe if I have a 16 by 16 image in RGB, I have about 1,000 features. That's not so bad. I mean, 1,000 features is doable. I go to a 64 by 64 image, I've got 12,000 features. I'm not going to say that's not doable, but it's starting to get a little bit tense. If I go to 256 by 256, I've got 200,000 features. I'm not really happy anymore. And if I go to like a modern HD camera or something like that, the problem hasn't really changed. But the higher the resolution, the worse my algorithm is going to get, which is kind of counterintuitive. You think, oh, let's get 4096 by 4096 images, and we'll be great. We'll really know that that's a cat, but it'll break everything. So what do I do in that case? I want something that is going to use the fact that this is an image and that there is a lot of redundant data and that nearby pixels are related to each other and things like that. And so that it doesn't have to learn a number of features that grows with the number of pixels, but it only has to learn something, fairly constant. So that was image data. Another example is sequence data. So here I just have some protein sequences. I picked short ones so I could actually fit them on the slide. And you notice, one of the things that happens here is they don't have the same length. So if I try to tabulate these, I could zero pad everything at the end. I could say, okay, the first n features are whatever they are, and then 0, 0, 0, 0, 0. And then I would have to have a number of features equal to the longest protein I would want to run this thing on, which I can do. But again, I'm paying this unnecessary price. If I just had something that could adapt to the fact that this is a sequence and that one thing comes after another and then it eventually stops, I would be better off. And the other thing is in these sequences, the index of the sequence is not necessarily that important. I mean, in these, it's not completely unimportant because there are terminal ends of proteins and things like that. But like, if I have a really long protein or even a sentence, let's say I have a book, I really don't want to have to make a classifier that uses the fact that this is the 8,000th character in the book to figure out what the book is about, right? If I add some text at the beginning, I now have to retrain the entire model from scratch because all the characters are offset. That's, again, not really the right way to handle that kind of data. And then we can get even more exotic. I might have social networks or metabolic networks or things where I have a bunch of elements and relations between them. And I have a variable number of elements and a variable number of relations, and maybe the relations don't all have to be the same type and may not actually fit into a standard typology. And then what do I even do, right? How do I turn this into tabular data in any way that's going to help? If I change the ordering of the elements, I should have the same network, but of course I'm going to have a totally different table. So now every single permutation of that table, I'm going to have to learn almost independently from each other. And the factorial function grows much, much faster than that cat problem. So, all right. There are two things you can do, and we're going to really heavily lean on the second one, but I'm going to mention the first one because this is what basically people did before about 2000, and this is the only thing that you could do before about 2000. If you came up with some statistical features, then you could make those into a table and then you'd be safe again. If I went back to the cat picture and maybe I said, I want the standard deviation of the pixels and the mean of the pixels, and I want some higher moment like a correlation function or something like that, then maybe I could just get away with that and I could throw out most of the picture, but those statistics would summarize the picture in a way that captures the catness of it or something like that. If I designed the features well, right? If I didn't design features that threw out the actual thing I'm going for. But that really depends on my personal understanding of the thing I'm trying to classify. And that's kind of moving away from what machine learning is getting us, of being able to actually have something that learns things that we miss. So yeah, sometimes that's what you have to do. For these networks, for example, people design a whole bunch of different kinds of graphs to try to understand and classify different kinds of graphs. And you could make a table out of those and then use traditional machine learning techniques. And the other thing you can do is now it's become really easy to use flexible frameworks. And what I mean by that is neural networks. And that's going to be more in Suzana's talk tomorrow to get into the details of neural networks. But that's not good. I want to show you different kinds of neural networks. I don't know why I put that. Okay, so for example, if I have tabular data, so the thing with neural networks is it's basically just a function, and it has to be a function that I can take a derivative of. But that's it. Right? I can talk about these things as neurons. I can talk about them as layers and so on. That's all just a convenient structure, but really all I have is differentiable functions that I can optimize that have parameters that are getting injected at different points. if I have tabular data, my function might be a matrix multiplication, and then some nonlinearity or something like that. And I just do this many, many times, and then I have outputs. That's fine. If I have sequence data, I could do something kind of similar, but I could say, okay, my rule is I have this matrix, and every time I go forward in the sequence, I take the previous thing I have, multiply by the matrix, and add in some information from the next character. And I just stop when I'm done. Right? So instead of defining like a table, I'm now defining a process by which I'm going to actually meet my data bit by bit by bit, and then my classification comes out of that. It's just another mathematical function, but it's a function that has this flexibility built into its definition, because I can do it 5 times, or I can do it 20 times, or I can do it 2,000 times, and it's really just, it generalizes, or at least the structure I've defined doesn't particularly have a fixed length in it, because it's doing it one character at a time, and it has this kind of relationship between that everything that's read up to that point is carried along in something that's keeping track. In a convolutional neural network, which is what's used for images, I just define some kind of local transform, which is this convolutional filter. It's a matrix multiplication, but it's now a matrix multiplication that is repeated at every location in the image on just the local neighborhood of that image. And that then takes each neighborhood where I applied that transform, maps to a new pixel in a new image, basically. And so this thing can apply to itself. And then if I want to summarize that entire image, I just need some way of making the image resolution shrink every time I do this. So I can use like a downscaling operation or something like that. And in the end, if I double the size of my input image, I don't have to change my network architecture or anything like that. Right? This is defined as for every pixel, apply this. So if I change the number of pixels, that's fine. It doesn't actually break the underlying structure of my algorithm. And that's the kind of flexibility that you get with neural networks that's kind of hard to find in some of the classical machine learning techniques. So, no, I mean, I guess there are a lot of different reasons why people use neural networks, and the simple one is they're very successful. They score very well. But I think like the really motivating thing is that you have this flexibility in defining exactly how you meet your data. So if I have some very weird data that just doesn't fit into a standard format, I don't have to completely reinvent the discipline every time. I just have to figure out what is the thing that makes that compatible. What is the kind of mathematical operation that lives on that space? Throw some parameters at it and optimize. So, okay. So that was the introduction to supervised learning. And I didn't talk about the details of any algorithm. Sorry about that, but I want to get people to the point where they can use it. If you want to actually get a better idea of the details, I would suggest reading the documentation of scikit-learn. This is extremely detailed, and you can pick whatever you want in here, and they will have examples in the documentation. They will, roughly explain how these things work. So this is a really good resource. I'm going to come back and sell this again. But for the time being, I want to get the workflow. So that was the intro to supervised learning. I guess I'll stop briefly here if there are any questions for the first half. I don't know if this is good or bad. Yeah.
In your one slide back, let's turn that there, it's fine.
This, yes.
Do people ever combine these systems like this? Because you've got downscaling, so potentially could you downscale to the point where you reduce tabular data?
Yeah.
And is that's the thing?
Yeah. So one thing you can do is I guess I didn't talk about pre-training yet. It's going to be tomorrow probably. I don't know if you're going to talk about pre-training. Okay. There'll be a little bit about it in the next section this morning as well. But like people will train these neural networks on giant image databases from Google. So ImageNet or there's a YouTube 300 million image data set thing now and things like that. So it might cost $10,000 to train one of these. I don't know. Then you have it, and what you can do if you have some new tasks, you can chop off the end, and these things downscale to the point, as you say, where you use tabular data, they would generate, say, 4,000 features. So you chop off the end, you take those features, and then you generally use another neural network to process them for your specific task, but you can use a support vector machine code. random forest or whatever you want. And if you do that, well, I guess hold on a bit and we'll see.
I'm not really sure if my question makes sense, but so when you show the CNN diagram, it's essentially a way to decrease the amount of data you have, right? So for example, if you originally had 9 pixels, now you change that to 1 pixel. So it decreases the data set, right? Every time you do that.
I would phrase it, I wouldn't say that it decreases the data size. I would say that it's processing the data in a piecemeal way rather than all at once.
Okay, so my main question is, for example, would it make sense to use some sort of, for example, SG filter or something also to reduce the unnecessary features?
An SG, like a Gaussian filter, or?
It's a statistically correlated.
Oh,
So for example, if you have if you have spectral data or time,
like, well, okay, yeah, like, so it turns out, generally speaking, if you just do that, the problem is you're actually throwing away information that was present. So the performance of the algorithm will often actually decrease if you just brute force filter, right? It would be like if I went and used the lower resolution image as the input in the first place.
Okay, so you're saying different.
This is different because it still processes everything that's in the image, but it just does so in a way that uses sort of the internal structure of the image to say, I don't need to worry about, say, doing everything all at once. I don't need to write the joint distribution between every single pixel and every other pixel. I can factorize that in a way that says, okay, first I'm going to get the local structure. Then, given that I've classified the local structure, I'm going to say how the local structures relate to each other. Then, given that I've done that, I'm going to say how those structures relate to each other. So it's hierarchically decomposing it rather than throwing out the high frequency. If that makes sense. So, like, now let's say I had a spectrum that had something like this, right? Okay. You might say, okay, I should filter this so that I get like this, right? But the thing is, maybe there's structure in this noise that matters. So I want to actually keep it. But I don't want to, if this is really high resolution, I don't want to just process it. So like, what is the value of this mass or this frequency? What is the value at the slightly epsilon different frequency? What I want to say is, okay, I have a sense of where noise is stored. I don't think that the statistics of the noise fluctuations here and the noise fluctuations here relate to each other. So I don't think the information is in that very long distance correlation function. But I think it's in a local correlation function. I think it might be in a correlation function with some exponential decay or something, right? So what I can do is I can say, okay, I'm going to pass all of this local data through something that actually cares about the individual jags of the spectrum. But then I'm going to summarize that. So I'm going to say, okay, maybe here the standard deviation is a function of the frequency or the wavelength or something like that. And that standard deviation is calculated over a small window. Or I might do something, I don't know, what's the kurtosis symbol? Well, anyway, I could have higher order statistics as well. And so then I'm not getting rid of this high frequency information, but I'm summarizing it in some way that it can still be useful. Right? This is me doing the first thing I described, designing the future by hand. How would I keep that info around? When I use the convolutional neural network, I'm letting the convolutional neural network keep. Yeah, exactly. It's discovering what would summarize the local data in such a way that when now I have a coarse-grained description of the spectrum, and maybe I have this, but I could also end up. I wouldn't necessarily just have one feature, right? I could have a bunch of features, and maybe this feature looks like this or something. And that's all learned from the data.
So you're saying this dimensionality reduction is in a way that
it's giving it the option to keep around anything that it thinks could be useful, as opposed to telling it what to use and then not letting it recover if we remove something that was useful, yeah. But it lets it make those decisions hierarchically. So it doesn't have to just get everything at once. It can actually say, first let's see, is there anything useful in the local structure? Now let's see, is there anything useful at the next order? Right? Kind of, I think it's probably, this is exactly what I guess the psychology of these things is a bit, it's not like there's a very clean answer yet, but this hierarchical idea at least is something that people used to think about what these things are doing. the thing that makes it a little bit more complicated is that, I guess now I'm getting to how neural networks work, but there's an error signal that is propagated back through the network. And that error signal first meets the data at the output. So often the really first, these high order statistical features are often the last thing that I learn, which is actually a little bit, a little bit the reverse of what I said. So that's a kind of subtle point. I hope that was useful.
Yeah, I think I understand that.
Anything else? All right, so this section is going to be more on, there's two goals for this section. One is if you're designing a machine learning project, let's say you want to get a postdoc or a student to work on something, is the thing that you're going to ask them to do reasonable, or are they going to come back and say, why did you make me do this thing? I'm not going to get my degree now, go away. So that's the first one, is it feasible? Like, is it well posed, and is it feasible given the kind of resources that you have? And the other thing is, let's say you're reading someone else's machine learning paper or a grant proposal or something where someone says, oh, we're using machine learning and AI, it will be great. We're going to actually be able to sample the life forms on the exoplanet using the computer as the telescope, and it will be perfect. And I want to give some tools of at least figuring out where they're lying to you. So there are a couple different things. In that, one is just the simple nuts and bolts of how are these things evaluated and how you can compare different evaluations. And then there are ways that these things can cheat or mislead. And I'm going to just go over kind of two. One is data leakage, which is when you're validating or testing on something, but somehow you let information from that test make it into the training method. And the other is when you're in the interpretation, when you're talking about correlation versus causation, which I keep harping on, I know, but it's probably the most important point about using these things. All right, so in science, at least, what I've encountered when trying to get machine learning things to be used with other scientific projects is people want to be able to test hypotheses or know what's true. So they want to say, did these two butterflies co-evolve to look like each other, or did one evolve to look like the other, or that one to evolve to look like that? I say, let's use machine learning to figure that out. Well, yeah. Similarly, people want to relate causes to effects. They want to know, if the early solar system were changed in this way, what would the modern solar system look like? That would be different. If Earth was not hit by a big impact and what would Earth's future be like, or something like that? What is the process that actually leads to this, chemical state on the surface of the Earth, or atmospheric state, or something like that? And they also want to explain or understand observations. So it's not just enough to say, here are all the exoplanets. Why are they distributed the way they are? Why is there a gap here? Or if there's a gap here, why would it be there? Things like that. So machine learning doesn't care about what's true. It just cares about matching the distributions that you give it. And so, the machine learning algorithm worked doesn't mean, oh, we know what is going on. It doesn't innately distinguish correlation from causation unless you do something very careful to make it really only be able to do causation. But it's not an intrinsic property of the algorithm that it can do that. And it doesn't make any kind of explanation in the form of referring to why. Why did I say that this is a cat? Well, because the 89th filter was greater than 0.2. Okay, we're done. That's cat. That is everything it knows about what it is to be a cat. So it doesn't connect things to a framework of concepts that you could actually talk with another person about intrinsically. You might be able to tease out details and interpret details, but that's actually what you need to do. It's not going to do that. So, okay, we're going to violate this principle all the time, I'm sure, because all the interesting stuff is pushing the boundaries of this. But as a default, don't assume that a machine learning approach will do anything other than optimizing the function you asked it to. And you hope that that is useful for something, right? You chose that function because optimizing that function should get me something that I want or should do something that I want. But if you're not sure about why optimizing that function would be, just because the machine learning algorithm hid the actual details of optimization, it's not going to actually make it something better than the idea of let's optimize this. So you really should make sure that the task you're specifying is the thing you care about, and it's also the entirety of the thing you care about. And I'll show you a kind of example. And the method really should be irrelevant if the problem is well formed. Like it shouldn't matter if someone uses a neural network or a support vector machine or a room full of grad students that they happen to have access to. Well, you might care about that because you might not be able to deploy that model, but at least in terms of the result, you don't really care if it comes from the grad student's machine. And you really should be able to verify it in the exact way you want to use it. You also have to be able to deal with approximate solutions because none of this will ever give you 100% accuracy ever. I mean, at least you should never expect it to. If you say this is only useful if I'm absolutely sure, then don't use machine learning, basically. So there's a Kaggle competition about plankton. And the idea here is that we, generally speaking, want to see how well the ocean biosphere is doing. But how do we actually tell what are the populations of all the microorganisms and things that live in the ocean? So you get a ship and you drag your camera behind it, and you've got whatever billions of frames of images. And they look kind of like this. And then you have students hand label it. So you've got someone whose degree is sitting in a room counting plankton. So it would be really nice to automate that so that we could basically have like a monthly survey of the ocean health, right? Get some cheap computers to do that. You don't have to feed them pizza. Neither the students or the machine learning are going to be perfect. So, we might want perfection, but we don't need it. We're certainly not using it now. And as long as we have some way of getting error bars and biases, then it can be used for future interpretation. And although someone who classifies this in a certain way might be able to explain why they did, in aggregate, when someone has gone through 100,000 of these images, they're not going to, the specific decisions that they made on the specific image are not really going to leave a signature in that aggregate data, right? If I just say, I had 50,000 of this one kind of plankton and 40,000 of that kind and 10,000 of that kind, I've lost the individual justifications for each image. And even if they did vary or I could know them, it wouldn't really be useful to do so anymore for that population data. So this is a problem where if I have a black box that just tells me what these things are, I'm happy. It's good. Another example is Google has been messing with detecting exoplanets recently. So you might have a lot of these light curves where you don't really know if there's it's not obvious that there's something there, but if you looked at it for a long time, you might be able to actually find that there's something there. And a lot of them will just not have anything there. So you don't want to spend a lot of time looking at the light curves that are empty or that have a very low probability of anyone ever detecting anything. At the end of the day, you're still going to have a human look at it, but you want the human to look at, say, 100th of the amount of data that they otherwise would. So you use the machine learning algorithm to throw out the things that basically have a very low probability of a human detecting something on it. Then you let the humans refine the ones that you keep. The problem, this is both good and bad. The bad part of this is you can introduce new biases. If the algorithm has a different sensitivity than the human at the end, you might discard systematically a class of planets that the human could have detected, in which case you now have this extra thing that you have to take. You can still measure this, right? Because you can still actually have the unfiltered thing, have a human do it, have the filtered thing, have a human do it, have the machine look and then compare basically what the statistics of what you find are. But you do have to take a bit of care. And this is a case that's not great in the sense that it's not like, okay, run the thing and then stop worrying about it. But it's something that's going to come up a lot if we're actually going to do really novel research, which is exploratory analysis. So you might have some really complicated objects that are not susceptible to human analysis. In this particular case, this is an embedding of different chemical networks. So I could have every point in here is a different reaction, basically, and I want to know how the reactions are similar or different. But the entire thing is this massive hypergraph that I just can't do anything with if I look at it by eye. So the point of this is that I could do this kind of analysis in ABC structure, but the fact that I ran this machine learning algorithm on it and got structure is not a scientific result yet. That's just something that would help me work with someone who actually understands the chemistry behind it to figure out what questions to ask in a more methodical way. The scientific result would actually come after the exploratory analysis, and that sort of leaves the exploratory analysis orphaned, at least in a practical sense. Like if I publish something about it, it should really be about the science that this led you to, but this is now also part of the process of getting there. So it might add something that you have to explain, but in the end isn't really important to the core story, right? I would have to explain, how did I get this weird tree thing from my chemical network? But in the end, I can't say that the X and Y coordinates of a chemical reaction really is telling me something fundamental about that reaction. I can only interpret it and say, we found some reaction class that seems to be different and doing something interesting or something like that. And yes, this is how I got there. So I think this is difficult, but not bad. I would encourage people not to necessarily discard this, but I think this is a case where you have to take care. It's not like hiring a student to do this might be a bit bad, but working with people to actually flesh this out, I think, is good. Okay, so I said you have to specify exactly and entirely what you want, and a very kind of toy example of people in reinforcement learning have been running into this thing that if you train an agent to, say, perform a task, it might perform some ancillary tasks on its own, whether or not you asked it to. So you might say clean up the toys, and it rushes, knocks over a vase on the way to clean up the toys. What you really wanted is the room should be clean at the end, but you said clean up the toys and it did that. It just had no care about what else happened that wasn't related to that end state. I'm not going to recommend anyone get into reinforcement learning, and this is a big problem in reinforcement learning and less of a problem in supervised learning, but it can still happen. Not exactly in this form, of course, but there could be things where, for example, you're trying to figure out something and it picks up on some methodological signal in the data. So like when we first did some stuff with exoplanets, what we found is that some people had, some of the data points had masses that came from observation and others came from a model. And so what the machine learning algorithm did is it figured out whether or not the exoplanet came from observation or from a model. Which, okay, it's kind of interesting, but in the end, like that's not actually a physical feature we want the machine learning algorithm to classify, right? So, this is kind of something to keep in mind. All right, so that, nice. Okay, that's enough. I'm going to show you the, I don't know if I can just put this here. Yes, there, approximate slide. So the big concern when starting a project beyond is it well posed? Do you have enough data to actually do anything? And I guess this is a really huge subject, and we could, each individual case probably deserves its own consideration, but at least for the classical approaches, roughly speaking, you need data linear in the number of features. So here I've got two problems. Here it was a linear problem, which is just two Gaussians separated, and then I added noise on every other axis. And then I have a fully nonlinear problem where all of the means of the Gaussians were the same and the standard deviations were all in random directions in a high-dimensional space. And in both cases, basically, as I increase the number of features, the algorithms get worse for a fixed amount of data. But I have this kind of linear, generally linear kind of region where the algorithm will go from completely chance level, which is in the red, to as good as it's ever going to get, which is the light blue. Similarly, for the nonlinear problem, same story. Chance level in the red to blue is the best it's going to get. Although notice that the linear algorithm here, this logistic regression totally fails everywhere because of course it just can't do it. So this kind of thing, maybe you need 10 times as much data as features, or maybe you need 3 times as much data as features, or half as much data as features. That might depend on details. But as you scale up the problem, you're going to need more data. So if we go to neural networks, this story becomes a bit more complicated. They tend to be slow starters, so you might need more data to get off the ground, but then they scale better. So those classical methods will get up to a certain point and then get stuck and then not really improve. But the neural networks, what people have found is that up to billions of data points, they continue to scale in accuracy roughly logarithmically. So if you double the amount of data, you get plus 5% accuracy or something along those lines. Not 5% in every case, it could be 1%, it could be 0.1%, but that's the scaling over speech, text, images, etc. But what we can do is maybe our specific problem is very narrow, like we want cat versus dog, and someone has solved a more general problem using other data. We might only have 100 images of cat versus dog, but they've done like, I don't know, cars versus trucks, and exoplanets versus stars or something like that, right? I keep going back to exoplanets. If they train a big network on that data, we can actually lean on that data to get some improvements, and that means that we actually might not need 1,000 points to get started. We might be able to do something with 10 points or 100 points. So here I just did there's a data set called CIFAR. CIFAR 10 in this case has 10 classes, and these are little tiny thumbnails. So there are things like toads and boats, I think, are in there, and maybe planes. And basically, if I just train a neural network directly on that data, I get this blue curve. So at 100 images, I'm almost chance level, and at 1,000 images, my accuracy is really, really bad. Still, it's like 40%, it's pretty much useless. Even by the maximum size of the data set, I'm only up to 75, 80%. I should say I didn't try very hard on this, and if you use the top of the line, state of the art, etc. stuff, this blue curve can get up to the high 90%. If you use a lot of tricks, but it's still going to kind of have, it's still going to need a lot of data to get off the ground. Then in orange, I just took a pre-trained network that was done on a data set called ImageNet, which is I think maybe 1 million images, and they're high resolution images, like I think the scale is 224 by 224 for this architecture at least. And it's got 1,000 classes, so it's got Pomeranians versus poodles in there somewhere, I think. And then when I train it on the CIFAR data set, almost immediately I start to see improvements, right? So by the time I've gotten 100 images, I'm doing as well as I had 1,000. And by the time I have 1,000 images, I'm doing as well as I'll ever do on the other method. So this kind of trick can basically reduce the data requirements. And if you have access to this kind of ancillary or associated data, it might make some problems possible that wouldn't otherwise be. But if you're doing something in a completely new domain, then you're going to be following this blue curve rather than the orange curve, and you're going to need enough data to kind of pump. So if you can find that other problem or find some other problem that could be related, that might be enough to help you get off the ground. Or even better, if someone's already solved a related problem, you can just download the network. But it's something to keep in mind. There's also data augmentation, where you sort of synthetically perturb the data to get more out of it. But I'm not even showing the curve here on this. It's almost exactly on the blue curve. It's slightly offset vertically when you do data augmentation. So it does help, but it's not quite as transformative as pre-training. Okay. Yeah, so as I said, let's say you have something and you've got a certain accuracy, but you really need, you've got 70%, and really for this application, you need 95%. So say, okay, no problem, we'll get more data, right? Well, yeah, maybe, but if you want to actually push it that far, the problem is the returns are logarithmic and the amount of data. So if you're Google, yeah, okay, you can probably get that 95%. It's only going to be a couple $1 million to do the data collection, I suppose. So this is something to really check and make sure that your scaling will make the thing you want to have happen possible. If it turns out, you can actually do a couple of resamplings of the data set size, and you can kind of project that curve and see, is this ever going to happen? Are we ever going to get enough data to actually do what we need? And for this, I think it's really important to say, sure, it's easy to go and take some data and throw it at the algorithm and see how well it does. But before committing a lot of resources and a lot of time to it, it would be good to actually start with the scientific goals and say, for these scientific goals, what is the accuracy we're going to need? Like, what do we actually need the machine learning to get to? And then don't worry too much about pushing far beyond that, because the costs are going to double every time you want to get a little incrementally better. And that will let you decide whether or not this is a project for a month, a year, an entire research lab for 10 years. Do you need a giant grant, or can you just do this on your spare time? But even the process of thinking, like, what would it mean to my scientific goals if this was the outcome, if this was the accuracy of the model, I think it's probably going to make it so that you don't end up with a machine learning algorithm and don't know what to say about it. So there are a couple machine learning problems that basically get talked about all the time. Image classification is the most common thing to talk about with machine learning. There's AlphaGo and things like that, of course, as well. Often these are things that a human, at least our expectation, could achieve 100%, but we believe that human performance is very close to 100%. We know it's solvable, and that people push really hard to get to where humans are, and that motivates the field to rush forward in those directions. That's fine if you're doing established problems. If if you're doing something in the image classification domain, yeah, you're gonna get good results pretty much. If you're doing something really new that people haven't done before, you might be working on a problem where human performance, peak performance, is not that high, and it may very well be that the actual ability of something, anything, the optimal algorithm to perform well on that is also very low. So that's a caveat. You could run into an impossible problem. And if you're in that kind of regime, more data won't tell at all. It's the information is simply not there in the inputs to get the outputs, is one thing that can happen. So it's something to keep in mind and be aware of, and look for that saturation behavior and kind of evaluate. The other thing is that human intuition doesn't really predict machine learning performance on the task. So if you think, how would I solve this task? Odds are the machine is not going to solve it the way you did. And very often the things that humans thought would be the easiest for computers were the hardest, and the things that humans thought were the hardest for computers were the easiest. So I guess my suggestion would be, like, take the results really seriously and, interpret them correctly. But like, if you're telling a story in your head about, oh, it's detecting the whiskers or something like that, it's probably, even if you can show that there's a whisker feature, it's probably not that it's detecting the whiskers. It's that maybe there's a statistical thing about whiskers that is contributing, but it's also detecting the fact that every cat photo is taken in warm lighting from overhead, whereas dog photos are outdoors, so they're cooler lighting the grass or something like that, right? It can do all sorts of things that don't fit a human intuition of how to solve a problem. So you really have to let the things coming out of the actual validation and so on kind of guide you in understanding what the algorithm is doing and what it can and can't do. If you think, oh, I would detect the geometry of the scene by looking where the shadows fall, well, that may or may not work. So, okay, that's is what I want to do reasonable. Should I believe it if someone says, oh, I made a thing that did this? Well, okay, one thing is to just keep an eye for basic statistical lies. So someone might report, oh, I have a 90% accuracy. That's great, right? Well, if we're talking about a medical data set, often it's 90% no disease, 10% disease. So 90% accuracy, that's chance level. If you just see that this number reported, it doesn't tell you anything unless you understand the data set that underlies it. What is chance level? What are the distributions of errors? Are the errors distributed in a way that is actually going to serve the purpose that this algorithm is being proposed to use? One way that you can kind of get around this problem, there are metrics that are less sensitive to things like class imbalance. So if you remember back, I showed this receiver operating characteristic curve construction. So if you make that construction, one metric that you can do is you can take the area under the curve. It's just called AUC. And if you have very imbalanced classes, chance level is always still 50%, which is this dashed line. So no matter what, if you don't know anything about the data, you can always achieve a 50% or a 0.5 AUC. So even if you have 99% of one class and 1% of the other, it's still going to be going from 0.5 to 1. So that at least helps a bit. So for example, here I just generated a fake data set where the 24 out of 25 labels are 0 and 1 out of 25 is 1. So chance level performance is, what is that, 96%? And this classifier is 97% accurate, which is great, maybe. Chance level is 96%, so maybe it's terrible. If I actually measure the AUC, it's 0.622 compared to 0.5 chance level. So, and you can in fact see what the curve is. So you can see that it gets about half of the true positives almost immediately, and it's a heavy. And then as you get the higher false positive rate, it doesn't actually pick up the par examples for a very long time. So it can get a little bit, but then it kind of stagnates, and you don't get much any more false positives until the very end. So this kind of thing, if someone is just reporting accuracy, it might be a bit hard to believe, or at least you have to understand the statistics of the data underlying to interpret it. If someone is reporting AUCs, you can trust it a little more. And if they show the curve, you can actually see exactly what's going on. Another thing is to worry about, if you remember back, I said there's two interpretations of probability that you can have. One is the actual rates of some kind of process, a generating process, and another is an inference or belief. Well, not every machine learning algorithm has what you would call calibrated probabilities. That is, beliefs given evidence that are kind of rational. So, for example, it might say, if you ask a support vector machine to give you a probability estimate, it's actually using something called plot scaling to kind of guess or to try to get the probabilities from statistics of retraining the classifier a couple of times. It's not actually part of the intrinsic algorithm to work in the probability space. So you find that if you say, how often does it say I have a 90% confidence in this point, it does so more often than the actual percentage of the time it's right about the classification of the point. So it might be right 75% of the time that says, oh, I have a 90% confidence. And you can detect that by basically plotting the frequency of how often it's right versus the probability that it gives of being right about that point. And different methods will basically have different kinds of calibrations. So like in this case, you also can see that there's a concentration of predictions. Right? You can essentially plot how often each of these is done. And one of the things that might be a bit surprising is Bayesian methods in particular. The mathematical formalism says that they're getting a kind of optimal belief, but almost always when you construct a Bayesian method, you are making assumptions about independence. So you're saying, okay, I have this X, this Y, this Z. In general, I should have the joint distribution between all of my variables and work in that space, but that's too big to sample. So you say maybe Z is independent of X and Y. So I'm going to write this as P of X comma Y multiplied by P of Z. And all of those assumptions always bias you towards being more confident than you should be. So you never can make an error of that form that makes you less confident. So Bayesian methods have a tendency, if they have any kind of internal structure, to push towards overconfidence in either a 1 classification or 0 classification. You can kind of see it here. The orange curve is naive Bayes, and it's got this kind of concentration at 0 and at 1. So in terms of interpreting the output of a model as a probability in the real world, again, this is something to keep in mind, that it might not be calibrated, and it might not even be possible to calibrate if you're predicting something where you don't have a true label.
Wait, sorry.
Yeah.
I have a question. So in that, the second figure,
Yeah.
If I have a point on the one on the X label, it means that it's X-axis. It means that when the model says it has a 100% confidence, it's right 100% of the time.
So in the bottom figure or the top?
The bottom.
The bottom is just how often does it say that it has a certain confidence.
Okay.
Right, so like a model that was always correct could have just a function, just have peaks at 0 and 1. But if you look at the curve above and relate the two to each other, then you can see that there's actually excess probability compared to the distribution of its actual accuracies. So,
thank you.
Does that?
Yeah.
Okay. All right. So the other thing is the distribution of errors matters. So you can say, oh, it has a 90% accuracy, but maybe for a subpopulation it has 0 accuracy, and for another subpopulation it has a 98% accuracy. And depending on the size of the subpopulations, that is something that could easily happen. But it would really, really matter if you deployed this thing in the real world, right? I have something that detects, stars, but it just completely fails for supergiants. But on average, it's pretty good, right? That maybe not so useful. So actually looking at the distribution of errors is important. And this is probably not using machine learning, but there's an example of like a soap dispenser that is basically calibrated towards a certain range of skin colors. And so, that caused quite a problem. But maybe on average on their test set, that matched the demographics of the test set. It just wasn't actually appropriate for how it was deployed in the world. So that's something to keep in mind if someone just reports a score, and where the distribution of errors could matter is that you might want to look at that and be critical of that. The other thing is how people choose their baselines. So if we're doing something in a domain where there's a lot of papers in that domain, there are going to be accepted baselines. Like if we're doing image classification, there's ImageNet, there's FAR, there's MNIST, et cetera. People say, okay, I know how to interpret a score on this data set because thousands of people have tried their best to really get the highest score possible. So that baseline has some weight behind it. But now let's say you're doing a new task, something that is it's scientifically interesting, but people haven't really done any kind of thorough work on it before. In that case, the author probably has to actually also generate their own baseline. So they might have to say, okay, 10 people have done crater counting, or 5 people have done crater counting. And we want to use a CompNet on it. So we're also going to try to fit a support vector machine or a random forest or something like that to it, just to say, oh, this is how much better the CompNet is. And problem is that when you do this, of course, the author might be a lot more motivated to get the CompNet to work well on that data than what they're using as the baseline. So especially with new things, it's kind of a problem because you want to be able to actually read research about new problems. But at the same time, you might not necessarily be able to have that kind of confidence of having a wide number of people all independently attempting the problem to judge just how much better it is. And it kind of means that, like, if you're asking the question, does this technique improve a method or should I do X or Y? That question is a lot easier to answer or easier to leave the answers in established domains. But in new domains, it's almost the purpose of the paper should be different in a way. It should establish that new domain is a problem more than, it's great if we use batch norm when we're doing these craters, or it's great if we use batch norm when we're measuring this chemical network property or something. In the end, though, there are ways of being more precise about what's causing differences in scores than just I have a baseline that I threw together and then I have my algorithm that's obviously better because otherwise I wouldn't publish it. So you do have to watch out that hyperparameter search is powerful. And so someone who has a giant cluster just trying things is going to get better scores than people who have less computational resources. So when you see something, if they report how much computation was used to get the hyperparameters, that can give you at least a bit of confidence that they thought about it and that they're actually doing some kind of comparison to see whether or not it's their actual thing. There's also subtle implementation details that often vary, or pre-processing details. If you look at the papers that have the best scores on SIFAR, they say we do data augmentation, but they don't actually say exactly what they do. And so if someone else did another method that got a better score or worse, is it because the data augmentation is better or because the method is better? A bit hard to say. And also, again, just an average error is not necessarily the most important thing. So what you can do to really get this precisely is to do ablation. And that's where you have your method and you remove one bit at a time of your method until you return back to your baseline. So for each thing, you kind of see what is the incremental gain that thing gives, or that at least establishes a bit more confidence in, oh, this change in performance is because of that, not just because I did 20 things and one of them was better and I'm just not clear on which is the better one. Okay. That's everything up to that was assuming basically like things are okay and just interpretation. Now we're getting to the things that are just an error has been made. So data leakage is annoying because it will happen and it will surprise you where it happens, but you have to deal with it. So, for example, let's say I've got a medical trial. I have 6 patients, and I've got a lot of data because I have electrodes on them for months. So I've got millions and millions of little fragments of EEG reading. Now I'm going to do a train test validation split. I mix all my fragments together and I take 20% for test and 80% for training, and I made a mistake. Because the thing that's going to be most informative is which patient it came from. And both the training set and the test set contain information about all 6 patients. So I have no ability to use this test set anymore to say, will this generalize to a 7th patient? If I really want to do this, I would have to actually reserve enough patients to be statistically significant, which with 6 patients is going to be hard. But in principle, that's what I have to do. There are other things I've seen, things where you do time series analysis and the data is like one long recording, but the experimental methods always have people do the labels in the same order. So there was this thing where you, a data set where you have an accelerometer on a phone and the person is like walking upstairs and then they walk over across the room, then they sit down in a chair, then they stand up from the chair. And every single time they do the experiment, they do the same order. But the data is just presented as one long time series. And so the really smart classification algorithm will just detect, oh, okay, I gave the chair class before, so now I should be giving this class, and just ignoring the accelerometer data once it's found out where it is in the sequence. So you have to be careful about that. Where are the actual directions of variation in your data that you care about, and what is the actual generalization test that you want to perform? And when someone else reports something, again, of course, keep an eye for that in their data. And then finally, correlation versus causation. This always seems to be the thing that we come back to. The simple thing is if I have some kind of thing like it's raining, so I carry an umbrella, it's raining, so it's a higher probability of traffic accidents, the machine learning algorithm is going to say, okay, well, I might not know if it's raining, but if I observe an umbrella, there's a higher chance of a traffic accident, right? It's actually not wrong, right? If I don't know it's raining and I observe that someone has an umbrella, then in terms of the optimal inference, there is a higher chance they'll be in a traffic accident because I can infer that it's raining and therefore I can infer that if they're in a car, right? So I can get that correlation. The probability in terms of how I should bet is correct. But now let's say, what do I do about this as a human who's reading the output of this machine learning model? Let's ban umbrellas. Yeah, no. And this isn't constructed to be really obvious, but when things get complicated and you've got 1,000 variables, and you make a machine learning algorithm to decide whether to give someone a loan, and you don't know what, you might even get to know what factors it's using, and you think it's not using something, but it's actually inferring it and then coming around from the side to kind of recover a label you excluded. You make a decision based on the output of that machine learning algorithm whether to give someone a loan or not. It's not necessarily going to actually work the way you think it will. It won't necessarily make it so that you have fewer defaults on the loans that you actually get or anything like that. So it's a lot of the times this is tricky. So here we go. There was a paper that was looking at people's faces to see if they're a criminal. Not like there's a specific person and we have a photo and we're trying to catch them in the population, but is there some general facial feature associated with criminality? And they report a 90% accuracy and along the lines of what I said before, this isn't just because it's a data set of 90% innocent people. Right? This is a data set that is balanced. It's 50-50, and they find that 90% of the time their algorithm can say who exactly ended up in jail in the next 3 or 4 years, or was in jail 3 or 4 years ago. So it turns out some of the images were from people's ID photos that were just like, this is a Chinese government data set, and it's just some ID photos of people. And then the other ones are the ID photos, still ID photos, but the ones that were chosen in order to make the wanted posters for these people. So, there's all sorts of stuff about how that choice was made that underlies this data set and what is the algorithm actually detecting. When they post a wanted poster, they're not going to pick a picture of someone who's smiling and happy. They want, right? Similarly, if these people are people who had just come from prison or were otherwise in prison, that's going to have an impact on, generally their, it's going to have demographic impacts, right? They might not be in as good of a position, they might have other things going on in their life, et cetera. So, what does this actually tell you? Like, what's the actual use of this? Aside from being very, very misleading. So it's, Yeah, so the interpretation of these kinds of models with respect to what they actually can and can't tell you is kind of something to keep an eye out for. All right, so having said that, is it actually possible to do causation with machine learning? And at least one way to do it is that you actually have data about interventions. So you've got your proposed medical intervention, and you try it, and you collect a data set that has a mix of cases where you've intervened and cases where you haven't. And now you can ask, what is the difference in the statistics between the interventional case and the non-interventional case? That's the simplest thing, that you basically cut the possibility of there being just pure correlation. So you guarantee that the thing you're predicting only has causation. And it's associated to having access to this random factor that you can control, right? So like the random controlled trial, you know that that thing has no prior cause. So if you see a correlation, that is causation. You can do more sophisticated things if you have some kind of constraint on how things influence each other. But it's a bit beyond the scope of this introductory talk. And if you want to get into that, I would suggest looking at Judea Pearl's Do Calculus, where there's a whole bunch of essentially rules for what you can and can't measure from a causal graph. But you do start to need to know something about the internal causation of the system you're studying, and you can make mistakes there. And machine learning algorithm can't necessarily pull that out on its own. Okay, and I think that's it for the morning. So if there are any questions, then thank you very much. Yeah.
So about this example of random quantity, what are we supposed to do?
Which? Yeah. So for example, let's say, yeah, it would be good to be concrete. So let's say we have something and there's a specific kind of cancer, there's a specific treatment where there's a medicine for it, right? So if you have, if you actually have data where you've given some people that medicine and you've not given that medicine to others and the trials are randomized and so on, then if you have something where you can train a model that says the probability of this having a good outcome when this demographic factor is there and the medicine was given, that's okay. Because whether or not the medicine was given is not correlated, or it's not being caused by any other factor coming out. But you would have to be careful to make sure that you aren't, because you are making a selection in the set of patients, right? In this case, it's people who have the disease that you're treating, and that's okay because you would think about giving the medicine to someone who doesn't have the disease. But in another case where you might give the medicine to someone who doesn't have the disease, it wouldn't be sufficient because now that choice of who gets the medicine is being caused by something else, right? So you have to be operating in a case where there's no prior cause. And if that's the case, then the prediction of the machine learning algorithm could be taken and validated and so on, and taken to be causal, and to decide whether or not they should be given the medicine. But if there is a prior cause, then you don't know whether it's just because they happen to have some common cause, right? Like it could be, say, type A to medicine outcome. No medicine. Right, this kind of thing's a problem. Like,
So basically, we should just take people that data that have cancer
you essentially have to make sure that the thing that you're probing, in this case, the thing you're probing is whether or not there's a link here. Right?
Reimbursement.
So you have to make sure that there's no error
Travel
coming to that.
No, we don't.
no higher value.
Yeah, nothing else about how you did it could cause that to take. So essentially, that the probability of medicine. The joint probability between medicine and sick type has to equal the probability of medicine times the probability of the sick type. Right? It has to be conditionally independent. Actually, I'm not. It might even be stronger than this because I think there might be. I have to think about it. There might be a way to have an arrow, but still fail this test. But I think this should do. Okay. And that's usually something you have to construct, right? It's not something you get to have handed to you. So for some questions, it would be really expensive, right? You could say like, I don't know, how should we design a society in order to achieve this outcome? So now we have to make a data set of 10,000 societies, in each of which we've changed in some systematic way how it's organized in a random way, and that's no longer feasible, right? So.
So when you prepare a data set for the learning model, to me it sounds like the negative data set control is really important. Because you know for the positive, you know exactly what you're aiming for, you know, you can probably pick all the positives. But then when you pick the control, like the negative data, there's two ways, right? Either you can do random sampling from all of the possible negatives, or you can probably bias those negative data sets to the way, for example, for this example you showed before, you can probably pick all the photos that are not smiling, for example. So you can probably put bias on the negative data set, but probably kind of change how the machine learning model and machine learning comes up with a model. So
that's what I was saying, that the most important thing is to try to generate the training data in exactly the same way you want to use the model in reality, right? So like in this criminality paper, what do they want to do with it, right? The thing that makes this a bit pernicious is that they say, oh, we're just curious if the machine learning algorithm can detect the kinds of social biases that people have or something like that, right? But that's not really an answer of what you intend to use this for. If you said, you know, like really starkly, we want to put a camera and arrest people who are going to commit crimes, right? It's not rational to say to do, or there's a lot of problems with that. Not just that the machine learning algorithm is bad, but if you were to say that's the goal, then you could see that this process is not appropriate. So a lot of it can be hidden in the fact that like you have data and you throw machine learning at it, but you don't think about where is the machine learning algorithm going to be used? What is it supposed to achieve for the person who's using it? And in this case, all it basically achieves is giving an excuse to arrest people who you don't like. Which, well, I guess you can do, but maybe it's presented in a way that suggests there's more to it.
So we need to pick the right data depending on the way of how we want the machine to answer a question.
Yeah,
I kind of get that. But there's also this the number of data set issue, right? Because if you want to pick the right data, but if the number of sampling points is small, then you kind of limit the data set.
Yeah, I mean, ideally you would have a pipeline that's giving you data, and then you make a transition over from a way of handling the data that doesn't use machine learning to the way you're using it. So that way you basically, the way you're acquiring data is also the same way you're going to use the machine learning. That's the ideal case, right, where I don't have to be clever to make it work. In reality, you might have a situation where the only thing you can get lots of is data that's sampled differently than what you actually want to do, and then you're kind of off in the woods. You have to try it on the real data, and it might just not work. And you have to have really good checks to make sure that it actually is doing what it's doing.
Yeah, so that kind of leads me to the second question. So if you have a hyperparameter, how do we actually, so if you use enough like machine power, probably the machine will pick the right combination of the hyperparameter that will get the best accuracy. But then the question is, how does human interpret the outcome of those combinations of hyperparameters?
I would generally, as I said, I think you want to design things so that you don't have to interpret it. Right. So if the scientific validity of what you do is depending on an interpretation of the hyperparameters, it feels like somehow there's a crossed wire in the actual design, because the hyperparameter doesn't necessarily mean something. Like in this case, it kind of does because the algorithm is really simple. But let's say I have a neural network, and the fifth layer, I find the optimal number of neurons is 83. It basically doesn't mean anything. It could be 7,000 or 154. And if I change the amount of data even a little bit, it could be an optimal. So I would say like keeping a clean separation between the things that the algorithm is doing in the black box and where the scientific interpretation is needed is kind of a key point.
I see. But if we want access to those black box, is there a way to do that? So, for example, feature in a principal component analysis, we know we can break it down to a single component. Whereas, is there a way to like for us to access to the hyperparameter, kind of like making conversion from these hyperparameter to the most similar component that we can?
I would say only in the exploratory sense and not in the sense of drawing a scientific conclusion. So you can look at, for example, in a neural network, you can look at what the gradients look like, or you can use the gradients to construct a strong stimulus that would activate a certain classification. And in the end, it's kind of cool. You can get an idea maybe what the network is doing, but there was a recent paper, for example, that showed that actually in image classifiers, maybe 2/3 of the performance is due to human recognizable features, and 1/3 of the performance is due to things that humans actually can't see. So that if you actually fix the network so that it can't use those features, the performance drops and it can't recover it. So if you just make an image of what kind of stimulus the network is using, that information might be there, but not actually in a way that a human can perceive. And you have to be very careful about, it looks like a butterfly, so that's how it's, but you can use it to guide your intuition, right? You can use it to look for things or to explore questions you could ask. It's just that the hyperparameters themselves they're not like a scientific hypothesis. You don't have a p-value and it's true, fundamentally true or false. It's just values that achieve an end. Okay, I guess let's have lunch and come back at